Hey, my name is Brian, and I'm a responsible AI engineer at LinkedIn. And on behalf of my co authors, I'll be talking about our work detecting and mitigation of algorithmic bias via predictive parity. And the high level view of this talk is that I'll be discussing a method of measuring predictive parity fairness, and especially how to do that once the samples are dependent. I'll be going over a quick application of how this looks when it comes to multi-objective modeling, and also hint at a case study of how we use this exact measurement tool to detect bias in one of our major models and mitigate it. But to give some background on predictive parity fairness first, the condition asks that we want the expected outcomes to be independent of the groups given the score. In other words, imagine that if a machine learning model predicted a score of 0.6, then you want that to have the same interpretation in terms of the expected outcome y, regardless of who the model is scoring for. And this is a desirable property in several settings, such as high-risk applications, where you want the model to have this output that have the same interpretation regardless of who it's scoring for. It's useful for downstream applications as well as marginal outcomes testing. It's also an intuitive notion of fairness that we use at LinkedIn for our predictive models, and it also aligns with traditionally modeling objectives such as AUC and MSE. To illustrate this as an example, let's say that we're in a world of binary gender for illustrative purposes, and say that we pass two people, Olivia, a female, and John, a male, through a machine learning model. Olivia gets a score of 0.85 and John gets the same score, but because the model is not well calibrated for males, the expected outcome given the same score is actually different. So you can imagine that if we now take these scores and put these people next to each other in a candidate recommendation algorithm, this means that John should actually be placed much higher somewhere because the expected outcome is higher. And so there are some issues in measuring predictive parity fairness currently. First of all, in binary group settings, this predictive parity condition asks us to measure the difference in the conditional expected outcomes. This is closely tied to ideas of calibration because if the model is equally well calibrated across all groups, then this condition is already satisfied. And in fact, predictive parity is often violated because some groups are worse calibrated than another due to, say, lack of data or distribution shifts. And we want to measure the difference in the expected outcomes. So traditional methods such as binning have been used to measure calibration error, and several recent works have tried to improve upon binning, which is known to be statistically biased, but it still focuses on measuring the overall calibration error as opposed to the difference, which is the fairness metric that we're interested in. And specifically, these methods also don't handle potential dependencies between samples. So to harp on that last point about dependencies a little more, the issues of testing under dependence can be illustrated as follows. Imagine that there's a lot of circumstances where you observe several dependent samples. So for example, if you're a popular user on LinkedIn, you may appear in a lot of people's feeds, or you may appear as a candidate for a lot of recommendations. And this can vastly skew fairness readouts if you ignore the dependency of samples. In this example here, the graph on the left shows independently drawn 50,000 individuals. And what we're going to do is just take 10 individuals from this chart, and then we're going to add 1,000 samples for those 10 individuals each. And you can see that the readout, even though we're only changing the data for less than 1% of the unique individuals, leads to vastly different readouts in terms of the fairness interpretations. And so this leads us to the main results of our paper, where we propose a modification of the Nadaraya-Watson kernel estimator that properly accounts for the dependence between individuals. If you want an intuitive feel for this, essentially, rather than one level of aggregation across all individuals, which is the standard kernel estimator for expected outcomes, we're going to first aggregate over all samples for each individual and then aggregate across individuals. And so we show in the paper some theoretical results about asymptotic normality, but the nice thing is really that this lets us measure the exact metric of fairness that we're interested in, which is the difference in expected outcomes, conditional on score. And we show multiple applications of this result for post-hoc calibration, marginal outcomes testing, and testing for multi-objective models. I want to harp on that last application a little more, predictive parity in terms of multi-objective modeling, because oftentimes in industry, these model scores are used in downstream applications. One example is a model score is used as a feature within another model. Another application, so-called multi-objective optimization, is you can imagine if there's two models that model different things like click-through rate or the number of sessions. One thing you might want to do is have a multi-objective optimization function, which is a linear combination of the two. And in the first case, predictive parity is nice because you want to make sure that if you're using the model score as a feature, that feature is equally informative, no matter who you're predicting for now. And in the second case, there has been some previous work that's investigated compositional fairness in ranking systems, but now we want to see if we can say anything about the predictive parity condition. And it turns out that indeed we can. If our multi-objective model is additive in the sense of a linear combination of the model scores, one thing we can do is jointly calibrate the scores with respect to the expected outcomes. And this is important because a lot of times this condition is violated because the scores and labels from different models are correlated with each other somehow. And if we follow the methodology that we explained in the paper, we can get a composition score that does satisfy predictive parity. So to illustrate this, say we have scores coming from 3 different models that have 3 different purposes, such as click-through rate, the number of sessions, or the number of post contributions. What we can do is essentially aggregate this training data and apply a joint calibration when looking across scores. And when we do this, we can be confident that when we see the same outcome score for different people or from different groups, we have the same candidate, we have the same expected outcome for the composite model. And so I want to end with a case study of how we use this at LinkedIn, because we actually use this exact methodology for testing under dependence to detect calibration gaps, which, as I hinted at before, can lead to problems in ranking. Our other talk, called Disentangling and Operationalizing AI Fairness at LinkedIn, goes into this case study in much more detail and also highlights some higher level principles that we take when we think about fairness at LinkedIn. But essentially, the story is that we use this methodology to detect predictive parity gaps, and then we also mitigate via a method that we explained in this paper, a non-parametric calibration method. And we also show in experiments that having predictive parity fairness can result in more fairness and also better product metrics. Thank you so much for taking the time to listen to our talk. We hope this gives you some view of how we think about and measure fairness at LinkedIn. And we welcome any feedback you have. Thank you.